So in many modern day rechargeable batteries, energy storage mechanism is based on ion intercalation reactions. So we have these electrode materials in our cell, and these have a layered structures. So how it works is that basically ions travel between these layered structures. So ions are stored and released from the space between the layers of these electrodes. So they kind of like shuttle between these layers, and the distance between these layers, this is called the interlayer spacing. So in our work, what we did was basically we investigated how changing this interlayer spacing affects the performance of the lithium-ion storage. And to be specific, we worked with vanadium pentoxide, and we used this approach of pillaring. So we used this pillaring approach to manipulate the interlayer spacing of our vanadium pentoxide. So how we did this was basically we inserted organic molecules between our vanadium pentoxide, basically alkyldiamines between these V2O5 layers. And what these pillar molecules do is that they act as spacers, so they hold these V2O5 layers apart. And we intercalated, or let's say inserted, diammoniums of different chain lengths, and by doing so we created V2O5 like vanadium pentoxides with different interlayer spacings. Importantly, we made sure that all of these samples had a similar morphology, a similar specific surface area, and a similar amount of pillar density between these V2O5 layers. And this way, we made sure that the only variable between these samples was the difference in the interlayer spacing. So basically, when we saw a difference in the electrochemical performance, we could say that this is coming from the differences in the interlayer spacing and not from any other factor. So there are many studies out there that have already shown that pillaring V2O5 can improve the capacity, the kinetics, the cycling stability of your cell. But there's a lot missing. So basically, what's missing is a deeper understanding of how these improvements are made. Like, why does pillaring change the capacity or the kinetics or the stability of our cell? So, for example, from a materials side, from a materials point of view, what wasn't clear was basically when you add these pillars into your host structure, how do these pillars react with your host structure? Like, how are they bonded? How are they lying inside the interlayer? Also, it wasn't clear basically how pillaring affects not just the interlayer spacing, but the intralayer spacing of your host lattice, and even the crystal structure. And looking at it from the point of view of electrochemistry, there was almost no information basically about how the lithium ions actually move through your system in presence of these pillars. Because if you think about it, these pillars actually act as obstacles between your layers. Even questions about like diffusion barriers, like the diffusion barriers your ions face when they travel through the interlayer, or about their storage sites, all of these questions basically remain unanswered. And this is where the novelty of our work comes through, because we tackle these questions. Most importantly, what we discovered was how the charge storage mechanism changes with the changing interlayer spacing. So basically, we noticed that if we have a smaller interlayer spacing, lithium ions intercalate alone, like as bare ions, into our electrodes. Whereas if we have an expanded interlayer spacing, we notice that the lithium brings the solvent molecules from the electrolyte along with it inside the electrodes. And this phenomenon is known as ion-solvent intercalation. So this is something that we noticed, and this is quite novel about our work. So, of course, after having synthesized our V2O5s with different interlayer spacings, basically this was actually done in a very simple one-pot hydrothermal treatment. And then we synthesized these materials with a small, an intermediate, and a large interlayer spacing. And then we had a look at the X-ray diffractograms of these samples. So we made use of an X-ray diffraction, and we measured the interlayer spacings of these materials, and we saw that we went from like around 1 nanometer to almost 2 nanometers in size of the interlayer spacing for these samples. We also used our simple electron microscope. So first we made use of transmission electron microscope, and we also made use of a scanning electron microscope to check the morphology of our samples. And yeah, we noticed that all the samples had this really nice nano-whisker-like morphology across all the different interlayer spacings. we also wanted to check what is the pillar content in these V2O5s. Like, do we have the same number of pillars depending on the chain length that we have used? And we made use of thermogravimetric analysis for this. Basically, we just burned the sample at a very high temperature, and we were able to calculate the chemical composition of our samples. Next, we also made use of gas option to check the specific surface area of our samples. We also made use of X-ray photoelectron spectroscopy to check the chemical bonding of these pillars to the host lattice. This was from a material characterization point of view. And for electrochemistry, we first started with the basic, our classic cyclic voltammetry and galvanostatic charge discharge. This was done to check the capacity, the kinetics, and the stability of our sample. We also made use of electrochemical impedance spectroscopy to check the resistance of our samples during cycling. And basically, after doing this, we established these basic differences in the samples based on the interlayer spacings. And then the question was, why do we see these differences? And for this, we made use of our in-house operando techniques. So we made use of Operando XRD first to check, to track basically the changes in the interlayer spacing during cycling. Then we made use of electrochemical dilatometry. This was done to measure the electrodes swelling on a macroscopic level. And lastly, we made use of quartz crystal microbalance. So it's an EQCM, which basically detects whether the lithium ions are intercalating alone or along with the solvent molecules inside your V2O5. Finally, we collaborated on simulations to identify the dynamic interaction between the intercalating ions, the pillars, and the host lattice with different interlayer spacings using some molecular dynamic simulations. So first, we investigated how the pillars interact with the host, and we found out that the amines from these diamines actually get protonated. So they are not amines in the end, they are ammonium ions, basically alkyldiamines, which get protonated, and they ionically bond with our V2O5 host lattice. And then we tested these materials in a cell. So what we noticed was that at a low current, the capacity was similar across all the samples. However, as you go to higher currents, basically at faster charging rates, the sample with the most expanded interlayer performed the best. Basically, it showed like the least polarization and the fastest kinetics. We noticed that we were also able to increase the maximum lithium storage sites. So basically, we saw that like when we go from a system where there are no pillar molecules, which also has a smaller interlayer spacing, we could only store 1 lithium per V2O5. This is an absence of pillars, okay? But then when you expand the D spacing, when you expand this interlayer spacing, we can actually store around 1.5 lithium per V2O5. So why does this happen? And we made use of modeling, and we noticed that when you go from a small to a larger interlayer spacing, the lithium pathways change. So basically, we go from a one-dimensional network to a two-dimensional network, and this makes diffusion easier and basically makes more active sites accessible, like there's more storage sites available. Having established this, we went to the Operando techniques, and this basically gave us the full picture, let's say. So what it showed us was that in a small or a medium interlayer spacing, lithium intercalates as a bare lithium ion. This is our classic solid solution intercalation. So you have your cell, and then there's your lithium ions in your electrolyte, which along with your solvent molecules, and then the lithium travels through your electrolyte. It goes to this interface between your electrode and your electrolyte, and the lithium ion basically strips off this solvent shell and then intercalates into your electrode material and takes part in the charge transfer process. But then when you just see the material with the larger interlayer spacings, our Operando technique showed us that lithium intercalates along with the solvent molecules. So basically what I spoke about earlier, this desolvation step that happens at the electrode and the electrolyte interface is skipped. So it just travels through the electrolyte along the lithium ion along with your solvent molecules, and it enters along with the solvent molecule inside your V2O5 with the larger interlayer spacings. And yeah, we also saw this unusual electrode swelling and a permanent expansion of the interlayer after cycling with the material with the largest D spacing. And Yeah, so EQCM results confirm this also. We saw the same thing, like when we have a smaller interlayer spacing, the mass change, the number that EQCM gave us corresponded with that of bare lithium intercalation, and with the larger interlayer spacing we saw that the mass corresponded to that of lithium plus solvent molecules intercalating. So to put it in a nutshell, we noticed that when you go from a smaller to a larger interlayer spacing, we change the mechanism from solid solution intercalation to ion solvent cointercalation. So far what we spoke about was we use these organic pillars that are electrochemically inactive. So if you think about it, they are actually dead weight in our sample. They don't participate in the charge transfer process, or they're not redox active. So what we would like to do is take this study one step further, and we would like to use bifunctional pillars. So basically pillars that not just hold the V2O5 layers apart and change the d spacing, but pillars that are also redox active themselves, like they can take part in the charge process, charge storage basically. And this would increase the energy density by storing more charge per gram in our cell. This would be one idea. Another idea that we want to take care of is basically we want to test different ions. So far we only we studied the intercalation of lithium ions, but we also want to study different ions like sodium or potassium, which have a larger ionic radius than lithium. And to take it one step further, we would also like to study the intercalation of multivalent ions like calcium, for example, which has a charge of 2+, and we would like to check how the mechanism changes and how is the charge process is happening, like what process happens, and we want to check this also. And yeah, finally we also plan to study how this co-intercalation depends on the electrolyte. Like, to be specific, we want to see how strongly the solvent molecules bind to the ions and how this changes the processes or the mechanisms.